Formal charges, it says in some cases we can draw several different Lewis structures that all obey the octet rule. The question is, which one is the most reasonable? This is very common in chemistry. So for example, carbon dioxide has two possible structures that you, the student, can draw. And we're going to draw it together, but I'm going to give you the possible structures. Here they are. They both satisfy the octet rule. They both satisfy the count, the valence electron count. But the question is, which one is correct? Is it this one or is it that one? Well, we need something called the formal charge to help us out. And there's a formula for helping you out, but then there's also a set of rules that we need to apply. The formal charge of an atom in a Lewis structure is the charge it would have if all bonding electrons were shared equally between the bonded atoms. So we say, okay, believe it or not, atoms, while some can be more electronegative, just want enough. They don't want too much electrons around them. They just want enough. Some can have more because they have a better, higher effective nuclear charge. But the formal charge is the number of valence electrons minus the number of non-bonding electrons plus the number of bonds. This is how you do it. It's a simple formula. You have to remember the number of valence electrons minus the number of non-bonding electrons, meaning the ones in the lone pairs, plus how many bonds each atom has. I'm going to show you also a shortcut. You may like it, you may not, but that's fine. So let's begin. So if you draw CO2, so here's CO2. You have C and two O's, 4 valence, 6 and 6. You add up these, you get 16 valence. So you have in this case, C in the middle, O's on the outside. And you start from the outside. Okay. So do you have any leftover? No. 8 plus 8 is 16. So you have no leftover. Well, what should we do if we have no leftover electrons? Well, we said we have to do double bonds, but you actually have two possibilities here. You have the possibility is, one possibility, and I'm going to draw it here, is taking a lone pair from each. So you'll have a double bond, two double bonds, or you'll have to take two lone pairs from one atom and you'll have a triple bond and a single bond there. So let me show you. You've probably already seen this. Okay. All right, come on now. So you have this possibility. And this possibility. Okay. The question is, which one is more correct? Well, we have to apply the formal charge. Here's how we do it. So start with each. So we say FC of, you have an oxygen, you have a carbon. Now, I can do the other oxygen, but if you look at it, this oxygen and that oxygen are equivalent, meaning that they have the same kind of bonding, the same number of lone pairs. So there's no need to do it twice because each is going, the answer is going to be the same for both. So we're just going to do one. And we're going to do the C. Okay, let's apply this. Let me erase this so we can have the equation. So let's apply this equation. It says the formal charge is the number of valence electrons. Okay. How many valence does O have? 6 minus the number of non-bonding electrons. Okay, meaning how many of those non-bonding electrons do you have? You have 1, 2, 3, 4. Plus 1, 2, 3, 4. Plus, how many bonds does it have? 2. 1, 2. Okay, so what's the answer? 6 minus, so what's 4 plus 2 is 6. That's a 0. 6 minus 6 is 0. So this is a 6. 6 minus 6 is 0. So we take this, put it there. Because again, this one is bonded the same way as that one. Let's go to this. C has how many valence? 4 minus, let's open parentheses here. How many non-bonding electrons does it have? Does it have any lone pairs, or how many in them? We have no non-bonding electrons, 0. Plus, how many bonds does it have? 1, 2, 3, 4. I know I don't want to run out of space here. Run out of space. So it's 4 minus 4 is 0. Very well. So zeros on all of them. Okay, let's do the next one, and then we'll look at the rules to know which one is better. Well, obviously here, we're going to have to do both oxygens because they are bonded differently. So I'm going to call this oxygen 1, and I'm going to call this oxygen 2. Let's start with oxygen 1. How many valence does it have? Valence is 6 for oxygen minus. How many non-bonding electrons does it have? 2, 4, 6. Plus, does it have any bonds? Yep, 1 bond. And that gives you, okay, 6 plus 1 is 7. 6 minus 7 is -1. Let's do the carbon. 4, carbon has 4 valence electrons, as we do with when we draw the valence, the Lewis structure, minus. How many electrons, non-bonding electrons, does it have? It has none, 0. There are no lone pairs on it, so 0. Plus, how many bonds does it have? 1, 2, 3, and 4. What's 4 minus 4? 0. Let's do oxygen 2, this oxygen. Oxygen, how many valence does it have? 6 minus any electrons in the lone pairs. Yeah, we have 2. 1, 2. Plus, how many bonds does it have? 1, 2, 3. Okay, so what's 2 plus 3? 5. What's 6 minus 5? 1, but we say plus 1 because it's a charge. A charge must be indicated even if it's not negative, it means it's positive. So therefore, this is plus 1 and this is 0. Okay, so you need to pay attention to these rules to discern which one is the better or the most plausible structure, reasonable, most stable, we'll say it this way. It says the sum of all formal charges in a neutral molecule must equal 0. And they do. 0 plus 0 plus 0 gives you 0, because remember, the formula of a neutral molecule is 0. The charge of a neutral molecule is 0. Same thing here. -1 plus 0 plus 1 is 0. Correct. The sum of the charges in an anion must equal to the ion of the charge. Not relevant here. But it says 3 is very critical. Small or 0 formal charges on individual atoms are better than large ones. Okay. Which of these has 0 charges, formal charges all? This one right here. 0, 0, 0. 0 means they're content. They have enough electron density that they're happy with that. And there's no separation, what we call separation of charge. So this one would be the better structure based on rule number 3. Rule number 3 clicks 0, 0, 0. Therefore, this is the correct structure. Carbon with 2 double bonds to the oxygens. All right. So what does this mean linguistically? Not just, by numbers. Math is helpful, of course, can't do anything without it, but we have to interpret this. This negative means this has plenty of electron density. This one is content. And that one means has less actually electron density, or sharing too many. This is sharing less, too little. This one is sharing enough. And that's the problem. So therefore, this is your structure.